Hi everyone. This lecture is going to cover chapter 10. The entire chapter is pretty short, 10.1 to 10.3 on Boolean algebra. So how, a lot of these math, you can do more complicated manipulation to it. That's then compared to what we saw in chapter 9. And let's start with some algebra, Boolean algebra. So Boolean algebra or binary algebra, right? And as I said, this is the simplest math possible. But we do want them to follow the same rules as decimal algebra. Um, so those of you who are, into math, so this is a binary number is a set, and then this particular set obeys the same um, algebra, the same sets of rules as decimal set. So that's why we want to make them the same. So, so this is hopefully a reminder of your first algebra class. I don't remember when this happened, right? So, algebra, when you do addition, is commutative. So that means, 1 plus 2 equals to 2 plus 1, right? In this case, A plus B equals to B plus A. So you can switch the order how you add. This shouldn't make a difference. And multiplication is also commutative, right? A times B is the same as B times A, right? And it also follows associative um, algebra where, if you have A plus the parentheses, if you do B plus C first and then add A to it versus adding A plus B together and then add C, it doesn't matter which order you do it in, right? These are rules that's followed by addition and multiplication, right? It's also followed the distributive rule, where if you have A times the parentheses B times B plus C, right? This distributes to both of them is the same as A times B plus A times C, okay? So these are the same rules that you have to follow, meaning the same algebra, right? That you have to follow in decimal, and we also have to follow, of course, in binary algebra, because otherwise, the math would not make any sense. There are also additional properties that's usually useful for binary only. So, for example, if you double bar, you take opposite twice, right? Opposite to opposite, right? It gives you the same number, right? So 1, if you flip it once, you get 0. If you flip that again, you get 1 again. So you get if any even number of nodding or inverting gives you the same state back. Then this applies to any algebra, right? Anything times 0 is 0. Okay. Anything times times 1, meaning the identity, right, gives you a self back. This is a squaring. A times A gives you A, because 1 times 1 always gives you 1, right? If you multiply it by its opposite, anything times its opposite will give you 0, because if A is 1, then it's 1 times 0, that gives you 0. If A is 0, 0 times 1 still gives you 0. Okay. If you add anything to it, it still gives you the same thing. If you add 1 to it, it doesn't take you out of the set. It keeps you as 1. And then A plus A has to be equal to 1, has to be equal to itself. So if it's 0 times 0 plus 0, 0 or 0, right, it gives you 0, right? 1 or 1 still gives you 1, right? And then if you have A or opposite of A, so meaning, like, let's say A is 1, 1 or 0 is 1, but if A is 0 is 0 or 1, right, because the opposite of 0 is 1, right, gives you 1 still. So these algebra follows for binary logic only, okay? So enforcing these algebraic rules gives us some interesting identities and theorems that we can come up with. So the last example in the previous lecture, in chapter 9, right, we show that basically if you have A bar dotted into, well, A bar and B bar right? These bars are separate. If you connect these bars together, right, you always have to flip the middle, and this is known as the De Morgan's theorem. Okay. The other way is also true if you have the or operator instead of the and, right? If you connect these bars together, you always have to change the and to an or. Okay. And we did this kind of using truth tables, and hopefully, if you need a reminder, make sure to watch 9 point, the last part of the previous lecture again to make sure that using the truth table, you can see, oh, this is the same thing. Okay. There are also other theorems. This is the absorption theorem, where you start with A, but then if you OR it with anything that's A and B, so it doesn't actually, you don't care what B is at all, right? That still gives you A, okay? Because the A dot B kind of gets absorbed into the OR of A. The opposite of that is also the complement of that's also true. If you have an A and parentheses the OR of A plus A and B, or A plus B in symbol, right? That still gives you A. So this part does not change your output at all. Okay, this is known as the absorption theorem. We're going to look at the negate and theorem, where if you have A and then negate and then and, okay, on B, it makes no difference. This part, right, makes no difference. If you have the opposite of A, you can literally just put that in and remove it as you like without changing what's the equivalent operation. Okay, so let's do an example to clarify why these theorems are useful. Okay, so let's start with the XOR gate, which is what the book example is. Right, exclusive OR gate, right, is only high if one of the input is high and everything else is 0. Okay, so A is high here, B is low, so that's why you get 1. A is low, B is high, that's why you get 1. Right, and the other cases with both of the inputs are high, right, you get 0. This is different from an OR gate because of that, right? And both inputs are 0, of course you get 0. Okay, and then the symbol for that is this, circle plus with a little exclusivity because you circle around it. Okay, what we can do is we can apply the negate and theorem from above. Okay, and what happened is that this plus here, right, we're going to use that for this, and what happened is that, well, if we have let's just write the equivalent that we want, right? A bar B plus A B bar. So what I did is I just added the A, okay, and then negated it, and then put it in front of the B. That should be the same thing as what we had before. And then I negated, I put a B, but then negated it, and with an and that should be equivalent to the right hand side here. Okay, and I'm going to calculate that. I'm going to check, is this the same as just the oops, only the this is the same as the exclusive OR gate. Okay, so let's calculate what we're going to make this big old table, and the book made it for me, so that's why I'm not going to copy it again. Right, so if A, so the 4 possible input is that, well, A and B are both high. A is high, B is low. A is low, B is high, right? And then both inputs are low, and that means the AND of A bar B, right? So this turns it into 0, right? Yeah, that's why this extra step is nice, right? So whatever A is, I want the opposite of it. The opposite is 0. 0 times B gives you 0. Okay, and then the next column over, right? Whatever A is, you just get 1. So, but then you want the opposite of B, or opposite of B is 1. Opposite of B, opposite of 1 is 0. That gives you 0 still. So the output here is 0. Okay, because there's an OR between them. Okay. And similarly, you can go through the same table, and then you're going to see that, well, you're going to have the exclusive OR output to be high, right? If one of the input is high, but not both. And if both inputs are low, you get 0 also as the output. Okay, so by doing this, you can see that, well, these two operations are exactly the same, right? So having a NOT gate in front of your input, right, in front of your input A, and then you put to an AND between them, and then you OR it with just the input A, and then the opposite of the input B, right? It's exactly the same operation as the exclusive OR gate. Huh. So, um, so this is where this kind of gets a little interesting to write, right? So not A and B, or A and not B, which is the second half of this, is the same thing as an exclusive OR gate. Okay, this is known as the exclusive OR expression. I don't know if people actually use it, but so why are we doing this? So that means if you don't have an exclusive OR gate in your kit, and you have two NOT gates, two AND gates, and a regular OR gate, you can build the same thing. Okay, so this is the circuit that allows you to build it. So you have two NOR gates here, right? The two NOR gates, right? Because you have your inputs here, and sometimes you want to take the opposite of A, sometimes you want to take the opposite of B, right? And you pipe those into an AND gate. These two are the AND gates, right? Right. So that's A and opposite of B, and this is opposite of A and B, right? The little dots in there. Okay. And then at the end, right, you put this through a big old OR gate, and then you get exactly the same thing as an exclusive OR gate. This doesn't seem very convenient still, right? Because then, well, you need like 3 different kind of gates to replace one. Okay. We can do a little bit more Boolean algebra with this and make it even more interesting. Okay. Okay. So what we're going to do is that we know that A bar, right? Whatever and of its complement. So if A is 1, the complement is 0. If you multiply them together, you always get 0. If A is 0, and then opposite of A is 1, right? You just multiply those together, you still get 0, right? Right. So A times A bar is 0, and then B times B bar is 0. What I'm going to do is I'm going to insert those in. Yeah, the book does it in 1 step, but I'll do it in 2 steps, okay? Right, we start off here, which is what we derived before. Okay, right, so I'm going to put the A bar here, okay, and then B, right, I'm going to factor it out, so plus, right, and then since this is A bar, I'm going to put an A here, because A bar times A is 0, right? Okay, but I literally just added 0 to the equation, just like what you do before in decimal math. Okay, and then A B bar. In that case, oh, B bar. I'm going to add A bar here, right? Once again, I'm adding 0 here, right? Because A times A bar is always 0. Okay, and that's how I get the next step here by just, rearranging things. Okay, did I do that right? Sometimes the bar, oh, they did the opposite. Okay, let's do that. Okay, because they always want the bar on the inside. Okay, so in this case, right, I want the B out here instead. So we have to copy the stuff down we had before, right? But then I'm gonna put B bar here because I know that B times B bar is actually 0. Okay, and then get this next step. Okay, this is sort of nice because, right, well, we can connect these bars together if we switch the OR to an AND. Okay, we can also connect these bars together if we switch the OR to an AND. So this is using De Morgan's theorem. Okay, and this is equivalent to this, right? Because basically I squish the two knots together and then I flip the or to an and. Okay. I'm going to do it one more time. Okay, since we have a or between them, if I put a giant bar across both of these terms, right? And notice that the bar only happens over some of them once and some of them twice. Okay, if I put a giant bar around this, I can switch this or once again to another and. Okay, and if I have enough bars, right, there's actually 3 bars over the entire thing. This is the third bar, this is the second bar, this is the original bar we already had. Okay, we can convert all those ors to an and to ands. In fact, the whole thing is actually a giant NAND because we're always getting the opposite of the result. Okay, we see just from the algebra, we see that, well, I'm going to try to read this out loud. Okay, the not of a times the NAND of AB, right, is times the, well, what, and then piped into the NAND of B, right, all that parentheses, right, NANDed together with the NAND of A and B once again. Okay, but instead of NANDing with B the second time, we NAND with A, right, and that whole thing gets NAND to each other. The result of those two outputs, those two intermediate outputs, gets NAND together. That is equivalent to an exclusive OR gate. Okay, so how does that physically manifest itself? Okay, so what you can do, well, we have A and B as NANDs once again. So we just pipe that into here, right? This is this, they actually share one gate. You can do the same thing twice. The output of this gets NAND with the input of B. I'm gonna do that in a different color, right? This level of NAND is actually this gate, right? And then this output is actually this top set of gates. Okay, still NAND gates. The outputs of those NANDs gets NAND again, right? So I'm running out of colors. I'm going to do red again, I guess. Right? The big NAND here is actually this final NAND gate. Okay, so basically what you can do is make an exclusive OR gates out of 4 different NAND gates by just doing a bunch of Boolean algebra with it. Okay, which is kind of nice. So basically NAND and NOR gates are known as universal gates. You can make do any logic any logic with them. Of course, we're gonna have, if you have both, then you can actually reduce some of the overhead because you don't want to have, to do a NOR, you don't want to have do 20 different NAND gates in order to do that. Actually, you need 20. You just need 5 actually. Anyway, so these are known as exclusive gates, and that's why a lot of companies, when they're making computers, memory or solid state drive, they either use NANDs and NORs, and that way they just built that one type of transistor circuit over and over and over again, and that's actually much easier compared to building multiple different kind of gates. All right, so that's kind of cool, and that's how you can play around to build different gates out of NAND gates or NOR gates. Okay, and we'll get to play around with that in the pre-lab and in the lab, actually, physically. The next thing I want to talk a little bit about is this Karnaugh map. This is very useful because what happens is that as you have more and more inputs, basically the size of your truth tables gets increased by basically the square of the n square. Basically, if you have 2 inputs, then the truth table is 4 rows. But if you have 4 inputs, the number of rows in your truth table goes up to 16. So this gets a little bit out of control, and then the Karnaugh map actually gives you a little bit better handle on the truth table, and it kind of gives you some algebraic relationship between them by just looking at, wait, what, some patterns on this Karnaugh map. Okay, so what we're going to do is going to show this relationship where A or B and A or C is equivalent to A or B and C. Okay, so there's three inputs here, and then what we're going to do on a two-dimensional paper, we're going to combine A and B together, okay, in the columns. But there's going to be a special way to do this, where we're going to do this following the grade-coded convention. That means you're only allowed to change one bit at a time. You cannot change 2 bits when you go from one column to the next. Okay, that means for AB, right, you start off with 0, 0. I'm going to change B to 1. Okay, but instead of changing B back to 0, right, which will go back to the original state, which will be redundant, what I'm going to do is I'm going to change A to 1. Okay, that's why 1, 1 is actually in the third place here. Okay, and then to get to the last possibility, well, I have 0, 0, 0, 1, 1, 1. I need 1, 0. I flip the B bit to 0, and therefore it makes it so that I cover all 4 possibilities following the grade-coded convention. Okay, so that's the top row here on this A, B, and then C can be either 1 or 0, so it's actually 2 rows here. Okay, so I'm going to do this thing on the left. I'll just do some examples. So let's just do the first column, first row, okay, where both A is 0, B is 0, right, and then C is also 0, and then hopefully the result is actually also 0. So A or B, right, since they're both 0, will give you 0, okay, and then A or C is also 0, and then the and between them is 0, so that's checks. Let's do one that's not 0. Let's do this last one here. Okay, so I'm going to erase this up here, right? Okay, so in this case, A is 1, B is 0. Okay, A is 1 or B, right? That's going to give you 1, right? Because one of them is 0. One of them is non-zero. A is 1, C is 0, so the or between them is also 1, and then you have an and between them, and therefore the and of 1, 1 is 1. Okay, and you can check the rest of this little Karnaugh map. Okay, but then if you do all 8, you see this pattern here, and the pattern we're looking for is actually either where there's a bunch of places with this bunch of zeros, or some pattern we see a bunch of 1s in one place. Okay. Okay. And the first pattern we see here is that, well, there's a bunch of 1s, right, around this box. I'm going to trying to figure out what's common between them, between all these 1s. Okay. Right. So notice that, right, for both of these columns, right, A is equal to 1. Okay, this is the A equals to 1 column. Okay, so what we're going to do is we're going to box this. We're going to call that A. Okay. The other pattern we see is that, well, there's something going on, right? There's also some 1s here. So then green, right? There's also a 1 down here. Well, 1 by itself can't really show a pattern there, right? What's special about that is that, right, in that case, this is on the bottom row, right? So that means C is equal to 1, okay? But the bottom row is not always have 1s in it, only in these last 3. So what's special about these last 3, right? Because if we extend it out here, what we can see here is that the second and the third row, right, is where we have B equals to 1. Okay. Okay. So that means these two here, right, is actually going to be B and C, right? Because if they're both 1, then they get 1s in both, okay? Okay, so there's an overlap of one box here, but that's okay, right? Because, right, remember when we do an OR operation, right? If we do an OR operation, we don't actually care if both of the inputs are 1, right? So this is actually A or B and C together, right? So the entire output here, wherever you get 1s, right, is actually in logic map, is actually known as the union of A and or BC, B and C together. So this way we can actually prove that, right, A or B and A or C is the same thing as A or B and C. Okay, so you could have done this using the Boolean algebra with a few steps, but this is just an example of how you can see this also on this Karnaugh map. Okay, this Karnaugh map gets more and more useful when you have more and more inputs, because it basically decreases the number of rows and columns in your truth table by a factor of square root of whatever number you ended up with. Okay, for example, this 4 input map. Okay, so you have A and B, right? Once again, we're following the gray-coded convention, whereas if you go 0, 0, you switch B first, right? Then you switch A, and then you switch the B back up to 0. You're only flipping 1 bit at a time. You don't flip 2 at a time. Okay, and then since this is 4 input, you put C and D on the rows, and then you follow the same gray-coded convention. Okay, and you start to see some pattern here. I'm going to erase these little arrows so we can see the pattern easily. Right, so we see all the 1s here, and then one thing to know about these Karnaugh map is that it's actually cyclic. Be a little careful, right? So whatever happens here is actually connected to what's on this side also, right? So what this is showing you is that, well, there's something, right, that's common between all these 4 boxes, okay? And the thing that's common between these 4 boxes is that, well, B is 0 here, B is also 0 here, right? B is 0, okay? And then C is also 0 there, right? Oops, not B. C is also 0, right? And then so what you see is that, well, it's actually an AND of the opposite of B and C, okay? So this is, and you label that B bar, C bar, but then B bar and C bar, okay? The other pattern you see down here, I'm going to do that in yellow, right? The book already highlighted it, but if you stare at these long enough, you'll see them, okay? In this case, right, the B's are actually equal to 1 there, right? However, right, in these rows is where D is equal to 0. So in this case, it's actually D bar and B that you're actually getting as the result. So by just making these Karnaugh tables with all these different inputs and outputs, you can actually figure out what the logical operations are being done on these on this particular circuit. So this is a way to kind of backtrack how the logic actually work. And if you ever look into a program to reverse engineering some circuits or even some programs, this is how they do that. It's by basically looking at the output and then backtracking how the code is actually written backward into the circuit themselves. Okay, so that's all. That covers chapter 10. So we'll see some pre-labs and some practice with this, and then we'll do a lab on it where we're first testing out some logic gates, and then constructing other logic gates out of them before we go into more complicated operations that we can do with these logic gates. Okay, thanks.